Welcome back to the deep dive. When you look at commercial aviation safety, there's one phase of flight that, well, statistically causes the biggest headache, and that's landing.
That's absolutely right. If you analyze the data, runway excursions during landing, they're the largest single category of accidents in air transport. We're talking about something like 20% of all reported occurrences.
20%? Wow.
Yeah.
That's a staggering figure.
It really is. And a number that big just demands a technical solution.
And our mission today is to take a really good look at the engineering response from Airbus, the Runway Overrun Prevention System, or ROPS.
Mhm.
And this is much more than just, say, a cockpit alarm.
Oh, absolutely. It's a full-scale intervention system,
Yeah.
really designed to combat that specific 20% figure.
So what's the backstory here? How did ROPS come about?
Well, what's fascinating is the context. I mean, RPS is a direct technical fix, sure, but it also came out of quite a bit of industry collaboration. It's partly a response to new performance regulations from EASA, that's the European Union Aviation Safety Agency.
Yeah.
And it also pulled in lessons learned from groups like the TALPA RC, the Takeoff and Landing Performance Assessment Aviation Rulemaking Committee. So it's kind of safety by consensus, in a way.
Right, built on shared knowledge. Okay, let's unpack this then, because ROPS sounds like it needs to be complex, simply because the problem it's solving is complex. What are those common things that can turn a normal landing into a potential overrun?
Yeah, the sources point to a real mix of errors and external factors. Probably the biggest single culprit is still the unstable approach, crews pushing on when maybe they should go around.
Relying too much at just feeling they can stop it, maybe.
Exactly. Believing they can recover rather than having objective, real-time proof that they can stop. It's that human factor trying to, well, bend the laws of physics.
And then you add the environment on top of that.
Precisely. Things like unexpected wind shifts, low down near the runway, or maybe the runway surface itself is wet, less friction than you thought. Then you have technique issues.
Like flaring too long.
Yeah, a long flare floating down the runway before touchdown, or late derotation, getting the nose wheel down too late. All these things just eat up vital stopping distance.
And I guess contamination is the worst case. Snow, ice.
Oh, absolutely. If the runway is contaminated, those safety margins can just vanish instantly. It's a really challenging mix.
So ROPS has to be this system that can somehow calculate the result of all those variables, like instantly. But before ROPS, there was another system, right? The foundation.
Yes, exactly. You have to start with brake to vacate, or BTV.
Yeah.
That was really the necessary technological starting point for ROPS.
Okay, tell us about BTV. What was its main goal?
Well, BTV was honestly quite revolutionary when it came out. But here's the interesting thing. While ROPS is all about safety, BTV was primarily about efficiency and comfort, actually. Its goal was more about logistics.
Logistics, how so?
So during the approach preparation phase, BTV would show the pilots the landing distance it predicted was achievable on the selected runway. This was based on, predicted data inputted earlier.
Right.
Then the crew could actually select a desired runway exit taxiway. And the system would then manage the braking, the deceleration, to ensure the aircraft reached that specific exit nice and smoothly at taxi speed.
Ah, okay. So BTV was about solving the puzzle of getting planes off the runway efficiently at busy airports.
Exactly right. It meant, increased passenger comfort because the braking was optimized, gentler. It reduced brake wear, kept temperatures down. You used the thrust reversers less aggressively.
And crucially, less time spent on the runway itself.
That was the big win for airports, yeah. Reduced runway occupancy time, which helps air traffic flow much faster. And Airbus basically leveraged this really precise, optimized deceleration logic to build the ROPS safety layer on top.
That makes perfect sense. Build a smart logistics platform first, then add the critical emergency protection. Okay, so let's transition now to ROPS itself. You mentioned it has two main parts.
That's right. Two core functions. There's the runway overrun warning, we call it ROW, which is really go-around oriented. It's trying to help the crew decide not to land if it's unsafe.
Okay, warning first.
And then there's the runway overrun protection, or ROP, which is stop-oriented. That kicks in on the ground if things are going wrong.
Got it. Let's start in the air then with ROW. When is it active?
Okay, so ROW becomes active from 500 feet radio altitude, RA, downwards, and it stays active right until the auto brake system actually engages on the ground after touchdown.
And what does the crew see? You mentioned lines on the display.
Yes, its main output involves these two really important lines displayed to the crew. Airbus defines them very carefully. There's the DRY line and the wet line.
Okay. DRY and wet. What's the difference?
The difference is critical, and it reflects sort of the operational thinking. The DRY line shows the landing distance the system calculates is achievable on a dry runway. Now, this assumes auto brake is set to high mode, assumes a normal landing technique, and importantly, it assumes only idle reversers.
Idle reversers. Why not max for the dry calculation?
Well, that reflects the standard desired way to land in good conditions. You want to preserve the equipment, optimize comfort. You shouldn't need max reverse thrust on a perfectly good, dry runway. So the DRY line represents that kind of optimized standard outcome.
Okay, so the DRY line is the ideal conditions calculation. What about the wheat line?
The WE line is, well, it's the more prudent scenario. It shows the distance achievable on a runway that's reported as wet. Again, it assumes auto brake high.
But this time,
it assumes the crew will use max reversers. This is the necessary operational adjustment you absolutely use maximum stopping power if the runway is wet or slippery. Both calculations also include some conservative margins, for system accuracy.
right, building in a buffer. Now, you mentioned something about a shifting calculation based on altitude.
Yeah.
That sounds like where the real intelligence lies.
It absolutely is.
Yeah.
This is where the technology really earns its salary, so to speak. Above 500 feet RA, the calculation for those DRY and WE lines is based on the predicted data, the stuff put in during approach prep, sort of textbook values.
Okay, based on the plan.
Exactly. But when the aircraft descends below that 500-foot threshold, that's the magic moment.
What happened?
The system completely switches its logic. It moves from predicted data to measured data. It essentially stops predicting and starts measuring what's actually happening right now.
It's like switching from looking at a map to looking at live radar and feeling the bumps in the road.
That's a great analogy. It becomes instant physics. Below 500 feet, it computes the landing distance based on the aircraft's actual current weight, its precise ground speed right then, the wind it's actually experiencing, the exact flap configuration, and its trajectory towards the runway.
So it gives the crew this live, objective calculation of where they're likely to stop. Takes the guesswork out.
Completely removes the guesswork, or at least it aims to.
And what if that live calculation shows the physics just aren't going to work? What do the pilots see on their main screen, the PFD?
Okay, this is where the alerts get serious. They escalate using color coding. If the calculated wet line moves beyond the end of the runway symbol, predicting you'd overrun if the runway is wet, that line turns amber on the display.
Amber. Okay. Caution.
Right. And the PFD shows a caution message. If wet, RWY too short. That's the first nudge, basically saying, hey, double check your assumptions about friction or be ready to brake hard.
And then the final, sort of abort the landing call.
That comes if the DRY line predicts an overrun. Remember, the DRY line represents the standard operation. If that line goes past the runway end, then both the DRY and wet lines turn red.
Red means stop.
Red means stop, or rather, don't start the stopping process here, go around. The PFD displays a very firm warning. RWRY too short. Here's the kicker. If this happens and the aircraft is simultaneously below 200 feet RA, a repetitive audio call-out starts. Runway too short, runway too short. The system is basically shouting, based purely on physics, that a go-around is required.
Wow, that's powerful. Okay, so let's imagine the crew either misses that call or maybe conditions degrade really rapidly right at touchdown. A go-around is off the table, now we're on the ground. This is where the second part comes in, the stop-oriented function.
Exactly. This is where Runway Overrun Protection, or ROP, takes over. It's the safety net on the ground. It activates the moment the auto brake system engages after touchdown, and it stays active until the plane stops. Its only job is maximum deceleration, trying to minimize the speed if an overrun looks inevitable.
How does ROP show the pilots what's happening during that rollout?
The main visual cue is something called the stop bar. It appears on the navigation display, the map screen. It's a green bar, usually, and it's highly dynamic. It constantly updates to show the system's best estimate of the remaining rollout distance.
And what's feeding into that calculation?
It's synthesizing everything happening right then. The actual ground speed, the deceleration rate the brakes are actually achieving, and the real-time braking conditions. Things like the calculated runaway friction, any slope on the runway, and how the anti-skid system is performing.
So it's not predicting based on approach data anymore? It's measuring actual real-time stopping performance on the ground.
Precisely. It's moved from prediction to reaction. And if that green stop bar starts to move past the depicted end of the runway on the display, meaning the system now predicts an overrun based on current deceleration.
That's the trigger point.
That's the trigger. The active protection kicks in. Visually, the stop bar and the predicted path turn red, and a stark warning message appears on the PFD. Max reverse.
Okay, visual warnings. But you mentioned active protection. This leads us to the really critical part, doesn't it? The automatic intervention.
Yes. This is arguably the most revolutionary aspect. If the auto brake system or the BTV system is selected and active, the moment ROP predicts that overrun, it automatically commands maximum available physical braking.
Maximum braking, like how much?
We're talking braking equivalent to the rejected takeoff mode, or RTO mode.
Okay, for listeners maybe not familiar, what does RTO braking feel like? What does it mean?
RTO braking is, well, it's the absolute highest rate of deceleration the aircraft's brakes are designed for. It's what you use if you're speeding down the runway for takeoff and suddenly have to abort at high speed. It's incredibly aggressive, punishing on the brakes, but potentially life-saving.
So the ROP system automatically slams on the brakes with RTO force during the landing roll if it thinks you won't stop in time.
That's exactly it. And the fact that the system does this automatically, even if the pilot hasn't commanded it, is a huge statement about where automation sits in a crisis. It can override certain prior inputs.
So the automation takes the most drastic physical action first, and then tells the pilots what else they need to do.
That's the sequence, yeah. The system applies max braking. Then, if it detects the pilots haven't selected max reverse thrust yet, a repetitive audio alert starts. Max reverse,
urging them to add engine braking.
Right. It keeps repeating until max reverse is selected, ensuring the crew is providing every bit of stopping force available. And there's one final safeguard.
Okay.
If the system still predicts an overrun even with max braking and potentially max reverse and the speed drops below 80 knots, a single audio call-out says, keep max reverse.
Why that specific warning?
It's to counter a common human tendency. Pilots sometimes start to ease off the reverse thrust a bit too early during the slow part of the rollout. This command warns against doing that if an overrun is still predicted. Keep everything deployed until you're safe.
It really is a remarkable combination of warning, visualization, and then direct, forceful action. Let's just clarify how this works in practice, because you mentioned it depends slightly on whether the crew used BTV for the approach.
Right, there's a slight difference. If the crew is using the full BTV ROPS mode, meaning they programmed the arrival and BTV is active, they get the whole suite, meaning they get the predicted DRY and wet lines above 500 feet, then the real-time lines below 500 feet, all the RW go-around alerts we talked about, and all the ROP functions on the ground. The stop bar, the automatic RTO braking, the audio alerts right from touchdown. Full functionality.
Okay, but what if they're just using the standard, classic auto brake modes, low, medium, or high, without the BTV preparation?
They still get protection, which is key, but it's slightly reduced. Since the system doesn't know for sure which runway they intend to land on until it kind of detects it automatically on very short final, the crew loses the visual guidance during the approach. So no DRY and wet lines displayed. However, and this is important, they still benefit from the raw audio alerts once the system figures out the runway.
Like the runway too short call-out.
Exactly. And crucially, all the ROP functions on the ground, the stop bar appearing after touchdown, the automatic maximum RTO level braking if needed, and the associated max reverse alerts, those are still available the moment auto brake activates. So you lose the early visual prediction, but you absolutely keep the ground protection safety net.
That distinction makes sense. It prioritizes the emergency stop capability, even if the predictive guidance wasn't fully utilized beforehand. Now, speaking of implementation, where is this technology actually flying, and where is it headed?
Well, RPS was initially certified for the A380 platform. That was planned through a software update expected way back around summer 2009, actually. But the plans for extending it really show the way Airbus sees future cockpits evolving.
What sort of extensions were planned?
Probably the most significant one is what they called manual ROPS. The idea here is to make the ROP ground protection available even when the pilots are braking manually without auto brakes selected.
So the safety net is there regardless of braking mode.
That's the goal. Removing the need to have auto brake engaged just to get that ultimate protection. This manual ROPS was expected for the A320 and the A330, A340 families around the 21-1 or 2012 timeframe.
And for newer designs.
And yeah, ROPS was slated to be just a basic standard feature on the then new A350 XWB platform, baked in from the start.
Extending that maximum safety intervention, that automatic braking, even into manual operations. That feels like a pretty big philosophical step, making this safety net almost unavoidable.
It really is. And looking even further ahead, studies were underway back then to extend ROPS capabilities to specifically handle contaminated runways better.
Meaning snow, slush, ice.
Exactly. To make the system even better at calculating the stopping distance accurately in those really challenging low-friction conditions, that would make it even more effective in truly extreme weather.
Okay, so if we sum up everything we've unpacked here, ROPS seems like this dual-purpose system designed to cut through the ambiguity in a landing crisis.
That's a good way to put it.
In the air, you've got the runway overrun warning, the ROW part, giving critical, real-time objective data to really back up that crucial go-around decision.
Helping pilots make the right call based on physics, not just feel.
And then, if that call is missed or impossible, you've got the runway overrun protection, ROP, on the ground. And it takes decisive, even forceful action, automatically deploying RTO braking to scrub off as much speed as possible.
So what does it all mean, really, for the pilot for safety? Well, the system provides that objective, quantifiable information below 500 feet, which helps fight that very human tendency to press on when maybe you shouldn't.
Right.
And then, in those absolute final seconds of a potential crisis on the ground, the system provides immediate objective force. It activates the most extreme braking the aircraft has, potentially regardless of what the crew has manually selected up to that point.
Which brings us neatly back to that provocative thought we wanted to leave you, the listener, with. We've established that the ROP system can automatically trigger maximum physical RTO braking if it predicts an overrun, right? Even if the pilots haven't manually hit the brakes hard or selected max reverse thrust yet?
Yeah, the automation takes charge of the braking.
So what does that reveal about the fundamental trust, or maybe the calculated lack of trust, between human pilot judgment and automated protection systems in these split-second high-stakes emergencies? When the system decides it needs to execute the ultimate safety maneuver, potentially overriding the crew's prior inputs, just to save the aircraft based on its own calculations.
It's fascinating, isn't it? The machine calculates the physics, predicts the outcome, and then acts decisively based on that prediction. It really makes you think about where the ultimate authority lies, or perhaps should lie, in a modern cockpit during those critical moments.
Definitely something to ponder. Thanks for joining us for this deep look into a critical piece of aviation safety technology. We'll catch you next time on The Deep Dive.